Good day. Um, we are going to talk about the nature of counting. So, this is different from our previous lessons, which were related to the nature of numbers. This time, we are going to learn more about counting, which is a fundamental use of numbers. Of course, numbers are not just for counting, but for many of the activities we do. Counting is an integral part of what we are able to do with numbers. So, what is the first topic? Let's first talk about permutations. This word you probably heard from your statistics classes. So, let's review what permutations is. In order to do that, let's talk about the election problem. Is could they elect a president and secretary? We call this the election problem. So there are several ways to solve this problem. The first and perhaps the easiest is to make a picture known as a tree diagram listing all the possibilities. So in here, the names of the members of the set are replaced by letters. So A stands for Alfie, B stands for Bogey, and so on and so forth. So it shows in the tree diagram that for president, there are five possibilities. So each member of the set has a chance to become president. So there are five possibilities at the beginning. And when we look at each entry among the five possibilities, for example, if we look at A, we now branch out four new names for secretary. And that's simply because the president cannot be the secretary at the same time. So if A were the president, then the possibilities for secretary are B, C, D, E, or the other names. So you list that down for A, and then you list down for B the four other names that could be secretary under President B. Do that for C, D, and E. And by creating a tree diagram, you will then count how many choices there are, how many possible situations there are for president and secretary. And if you look at how many chances there are in this tree diagram, you will find that there are 20. So the answer is 20. How many ways could they elect a president and secretary? The answer is 20. We see that there are 20 possibilities for choosing a president and a secretary from five club members. This method is effective for small tree diagrams, but the technique quickly gets out of hand if the guy, if, for example, if we wish to see how many ways the club could elect a president, secretary, and treasurer, this technique would be very lengthy. A second method of solution is to use boxes or pigeonholes representing each choice separately. Here we determine the number of ways of choosing a president and then the number of ways of choosing a secretary. So there are, in the first pigeonhole, we write the number 5 because there are 5 ways of choosing a president. And then for secretary, we write the number 4 because since we have chosen a president, only 4 names remain. Then after that, we multiply the numbers in the pigeonhole. So 5 times 4, we get 20. And we see that the result is the same as from the tree diagram. A third method is to use the fundamental counting principle. So the fundamental counting principle gives the number of ways of performing 2 or more tasks. If task A can be performed in m ways, And if after task A is performed, a second task B can be performed in n ways, then task A followed by task B can be performed in m times n ways. So we multiply, right? So let's look at another example. Determine the number of ways of choosing three. In how many ways could the given club choose a president, secretary, and treasurer? So using the pigeonhole method, well, we start off with five possibilities for each of those members to be president. Then if we already chosen a president, there are four names remaining who are qualified to be secretary. And after choosing a secretary, there are only three names remaining to choose from as treasurer. So the answer is 5 times 4 times 3 or 60. So there are 60 ways of which this could go about. Like A could be president, followed by B, the secretary, and C, the treasurer. That's just one possibility. And according to our calculation, there are 60 possibilities. When set symbols are used, the order in which the elements are listed is not important. Suppose now that you wish to select elements from A equals A, B, C, D, E by picking them in a certain order. Oh, so what if a certain order is required? Then the selected elements are enclosed in parentheses to signify order and are called an arrangement of elements of A. So if we change the braces into parentheses, that implies that the order matters. For example, if the elements A and B are selected from A, then there are two pairs or arrangements, AB and BA. So those are now two different things because the order matters. These arrangements are called ordered pairs. Remember, when parentheses are used, the order in which the elements are listed is important. This example shows ordered pairs, but you could also select an ordered triple such as DCA. These arrangements are said to be selected with. If we are given some set of elements and we are to choose without repetition a certain number of elements from the set, we can choose them so that the order in which the choices are made is important or so that it is not. If the order is important, we call our result a permutation. And if the order is not important, it's called a combination. So now we consider permutations. Suppose we consider the election problem for a larger set than A. We wish to select a president, secretary, and treasurer from here. There are six names: Frank, George, Hans, Iris, Jane, and Carl. We could use one of the previously mentioned three methods, but we wish to generalize, so we ask, is it possible to count the number of arrangements without actually counting them? In answering this question, we note that we are selecting three persons in order from a group of six people. If an arbitrary finite set S has n elements, and R elements are selected without repetition from S, where R is less than n or equal to n, then an arrangement of the R selected elements is called a permutation. Okay, let me repeat that. A permutation of R elements selected from a set S with n elements is an ordered arrangement of those R elements selected without repetition. Let me ask this example: number of permutations of 2 chosen from 6. How many permutations of two elements can be selected from a set of 6 elements? Here the order matters, so that choosing the first then followed by the second is different from choosing the second then followed by the first. So it's the same two elements, but since the order matters, so they become two different answers. So let solution let B equals A B C D E F and select two elements. So first selection is AB followed by AC, AD, AE, AM. You go over all the possibilities and noting that the order matters. So AB is different from BA. So if the order doesn't matter or combination, then this list would be a lot smaller. But since the order matters, we see we have a lot more ordered pairs. In fact, there are 30 permutations of two elements selected from a set of six elements. So for permutation where the order matters, the symbol NPR is used. The number of permutations of R elements selected from a set of N elements. So N here is the set of how many elements there are in a set, and R is how many elements do we select out of that set. Two for ordered pair or three for ordered triple, whatever. How about this? For example, I'll evaluate from a set of 52 elements, we take two ordered pair, we take an ordered pair, and the order matters. So to do this, we use the fundamental counting principle. So why is this? So we start off with 52 possible elements. So we choose one. And then for the second choice, we only have 51 left, 51 elements left since we already chose one originally. So we use the fundamental counting principle. 52 times 51 equals 2652. 7p3, this means that there is a set with 7 elements and you get 3 out of each set, like an ordered triple. This is kind of like selecting a president, then a secretary, then a treasurer. So you start off with 7 possibilities for the first choice, and after your second choice, only 6 possibilities remain because the first one has already been selected. And for your third choice, you have 5 possibilities remaining since the first two have already been chosen. So 7 times 6 times 5, that is 210. 10p4, so now you get the idea, right? We can use the fundamental counting principle to solve for the permutation. So this is the formula. So let's talk about the factorial. Yeah, so in our work with permutations, we will frequently encounter products such as 6 times 5 times 4 times 3 times 2 times 1. So as you can see, the number is in descending order. So these are rather lengthy, so we use factorial notation. So for any counting number n, the factorial of n is defined by n factorial equals n times n minus 1 times n minus 2 times all the way until we reach 1. Also, 0 factorial is equal to 1. So right, 2 factorial is 2 times 1 equals 2. 3 factorial is 3 times 2 times 1 equals 6. 4 factorial is 4 times 3 times 2 times 1 equals 24, and so on and so forth. How this is a complete list. Notice that these numbers get really big, no, really fast. Um, that's why I guess that's why they use the exclamation mark for the notation of factorial. Because 52, if you can see 52 factorial is so big that it is around 8.0658 times 10 to the 67. So if you actually carry out that calculation, you will arrive at a very large number. Um, we have this property of factorials that, for example, 3 factorial is equal to 3 times 2 factorial, right? Because if you expand 2 factorial, you get 2 times 1. And 4 factorial is equal to 4 times 3 factorial. And that's a useful property because in some situations, you will be able to really simplify your solution, especially if the number factorial appears in both the numerator and the denominator, and you can cancel those out, and you will really leave your expression truly simplified. This property is called the multiplication property of factorials or the countdown property. So n factorial is equal to n times n minus 1 factorial. So let's evaluate the following factorial expressions. Okay, for letter A, what you just do is you just evaluate 6 factorial, and that is 6 times 5 times 4 times 3 times 2 times 1. Apparently, that is equal to 720. And 4 factorial is equal to 4 times 3 times 2 times 1, which is equal to 24. So letter B, 6 minus 4 quantity factorial. So all you have to do is to simplify the expression inside the parenthesis. 6 minus 4 is just 2, and 2 factorial is 2 times 1, or equal to 2. This one is very useful. Here you are using the countdown property to realize that 8 factorial in the numerator is just 8 times 7 factorial. Now you have a 7 factorial both in the numerator and the denominator, so you can cancel both out, and what you're left with is 8. 12 factorial over 9 factorial. Again, we can use the countdown principle. 12 times 11 times 10 times 9 factorial. So then you can cancel that out. You are left with 12 times 11 times 10 equal to 1,320. Here, similarly, for 100 factorial, we count it down until we reach 98 factorial. And so you cancel that out because in the denominator, meron ding 98 factorial. So you are left with 100 times 99, or 9,900. So using factorials, we can find a formula for the permutation. Recall that permutation is n times n minus 1 times n minus 2 dot n minus r plus 1. So actually, I will not go over the details of this um, derivation, but you will find eventually that the general formula for getting the permutation is found here at the bottom. N factorial over n minus r factorial. So again, n here is the number of elements in the set, and r is how many will you get at a time from the set. So this is the formula for permutation. NPR is equal to n factorial over quantity n minus r factorial. Distinguishable permutations. We now consider a generalization of permutations in which one or more of the selected items is indistinguishable from the others. So what is this? How about this, no? Find the number of arrangements of letters in the given word. Math and hath. Solution. This is a permutation of four objects taken four at a time. True, that's correct. So arranging letters, right? The number of arrangements of letters in the given word. So you can start with the obvious MATH, but you can also select MTAH and then MHTA. There's a lot of possibilities, but we can actually calculate it. And what we get here is 4 factorial equal to 24. If we use the formula that we learned, if you go back, is n factorial over n minus r factorial. So in this case, in the case of math, right? So, and our n here is 4, but our r is also 4, right? So what happens to the denominator is 4 minus 4 equals 0. So what happens is in the denominator, it becomes 0 factorial. And if you recall, 0 factorial is just equal to 1. So that's what happened here. 4 factorial na lang nabilin. 4 times 3 times 2 times 1. Also, this obeys the fundamental counting principle, right? You start with 4 letters, and then after selecting the first letter, you now have only 3 choices of letters left, and then followed by 2 and 1. Now for letter B, there is a dilemma here because the word is hath and there are two H's, and the first H is indistinguishable from the last H. Both are just H's. So how do we solve this? This is different from part A because not all the letters in the word hath are distinguishable. That is, the first and the last letters are both H's. So they are indistinguishable. So if we make the letters distinguishable by labeling them as red H, AT, black H, we see now that the list is the same as in part A, right? So if H red is different from H black, then this is just a permutation, 4 by 4 permutation, and we should get the same answer as part A, or we should get 24 possibilities. But notice how we have arranged the listing, right? However, if you consider red H to be equal to black H, that is, the H's are indistinguishable, we see that the first and the second columns are the same. Right. Oh, right. The first and the second columns are the same. Hath, hath, hat, hat. So, since there are two indistinguishable letters, we divide the total by 2. Oh, really? So 24 divided by 2. So I think what happened here is that since you are selecting 2 at a time. Oh, anyway, this is just the formula. So the number of distinguishable permutations of n objects in which n 1 are of one kind and 2 are of another kind and nk are of a further kind, so that n equals n plus 1 plus n plus 2 plus dot 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 plus nk is denoted by n over. Oh, this one is too complicated, right? So anyway, that's the end of our